2004, 2008, 3000C. So now in that next line, when you say star C equals star ampersand C sub 3, first this is just a trick, right? So that's just going to be C sub 3. You're using the new base address. So this star C is there. Dereference the current value of C you get here. And here this is the same thing as star C plus 3, right? So I start at the base address and go down 3. So, you know, essentially it's like C sub 6, sorry, C sub 3 equals C sub 6, right? If you hadn't changed them, see, if you're sort of using these things. You know, another way to think about it is that the address that's being, so we can talk about it without referencing the array, is saying the address that's being written to is C300C, and the address that's being read is whatever that is, 318, 3018. Does that make sense?
After changing the base to C sub 3, would you still be able to access like C sub 2?
Yeah, so what if you wanted to get this one after you make that change? What do you think you would do? Yeah, so this is, again, just totally bizarre, right? You can do that, no problem. Because it's the same as pointer subtraction. Subtracting an integer from the pointer. That's the same star C minus 3. Perfectly fine. So you can see actually, we actually talked about this when we talked about array bounds checking, because you have to, in C you have to check, you have to actually do this in Java too, because you don't know the value of an integer, but you have to check underflow and overflow, even with constants.
Where does 3000C come from?
3000C came from the first line that said C equals the address of C sub 3. The address of C sub 3. So what's the address of that? That's 3000. That's 3004. 3008. 3000. It's 12, but in hex. Okay.
Then does the compiler take care of all the switching from index-based to offset?
Yeah, the compiler totally takes care of actually producing the right addresses when you express things in index.
It was based off of type, then
Exactly, based off. Yeah, so if you change the type of a pointer, you change from int star to char star, and you add to it, you're only adding 1. Not 1 times 4. Other questions? Okay, so is that clear? Do you want me to spend any more time on that? Who would like more time on it? So the rest of this just goes through that in more detail, showing the assembly language to convince you. What's really important here is to see that when you access an array, you're just, it's a dynamic array, you're just reading whatever the current value is. All right, so let's move now. Just get started in the next, which is about objects, essentially. So here's where we are. We've got static and dynamic arrays. We've got also scalars. We talked about the advantages of static is the compiler knows the address of things, the code it generates for access is runs a little bit faster. But the advantage of dynamic is that you can size arrays based upon calculations the program does based on inputs to the program. Usually we're going to use dynamic arrays with most things just because you get that flexibility. And both of these variables are declared in file scope. They're global variables. So we're not going to look at variables that are not global variables. So these in Java are variables that are declared inside of a class without the word static. Right? So if you look at the red box up there, there's a class X in Java that has two variables, static int I and int j. So static int I is in the class. There's just one copy of that. J is not in the class. All the instance variables form a template that's used to stamp out objects when you say new, as you know. So if I say new X, I get an object, and the object contains the variable J. But I don't refer to that variable J just with J. I have to refer to it relative to an object. So I have some object that's the reference to a distorted variable like an X. I say an X.J, I get that particular J. But there's actually many J. I can say new, and I have different variables pointing to different objects. Each one of them has a J. Does that make sense? Right? So this is a variable that, of course, the compiler can't allocate things when you say new. This is statically allocated. These variables, the variable itself, has a lifetime that's dynamic. Initially, when you start the program before you say new, there are no J's. Even though you say class J, there's no J's until you say new. So we have something like this. It's a bit different, but can do all the same, most of the same things without the object-oriented typing. In C, it's called a struct. Structs are the building block of classes in C++. In C++ also has structs, and C++ has classes, and classes add types and methods to structs. So if we just looked at the instance variables of a class in Java, this is the same as a struct. So you say struct, then you can give, it's optional, you give the struct a name, and then you list inside it a collection of variables. The variables can have different types, and they must have different names, of course. It's actually very important that you put a semicolon after this, which is strange because in most languages the squiggly bracket implies a semicolon, but not in this specific case. And what that does, after you say that, there isn't an E or an F. This is just a template for creating E's and F's. It's a type. So in Java, which is on the right, when you say class D, you've declared a type, and the name of the type is D. So you can declare variables D, and then some variable, right? In C, the type name is not D, it's the full phrase struct space D, struct D is the type. And so, if I want to declare a variable that can point to objects, to structs, I do it like this. I say struct D star. So if I say struct D star, struct D star D1, I create a box that can store pointers to the struct. I then would have to say malloc, just like with arrays. When you say malloc, I can say size of struct D to get the number of bytes, because the size of that struct is known statically, so I can do that, or I can, the size of that is how many bytes. How big is struct D? 8 bytes, so I can just say malloc 8, right? And having done that, then I would have a struct. And the struct has E and F, right? E and F. And this would point to it. Just like with arrays.
Does the size of operator work with the struct?
Yes, the size of operator will work on anything whose size is known static. So you can say size of struct B. We'll talk more about that. Some other things you can do too that are even better. Now, In Java, when you do this, so the Java equivalent of this is essentially, I want to be writing black, but I put the black, it doesn't matter. It's black cap on the blue pen. And now I'm writing blue. So in Java, you would just say D. No star. And the reason for that is that all of these expressions for variables in Java, as we talked about, we were talking about there's pointers and references, are references. They're of this form. You can't do this other thing that you can do in C, if I leave that off. No star, then just like the static array, I now have a static struct. Okay, so now, if this was an array, everything's the same, and I would reference elements of the array using the same syntax. Right? I can use either the star syntax or the square bracket syntax. But here's where the designers of C, I don't know, they went out for lunch and had too many beers or something, and they came back, and they decided to make the syntax of these two things different. So here's the enough. So if you have a static struct, you use a dot, just like in Java. But Java is not a static one. If you have a dynamic one, which is what you have in Java, you use an arrow. Now there's other languages, the Pascal modular languages all use arrows for references. So it's actually common, it's been common. So that's sort of, there's a kind of consistency here that Java broke because they didn't want you to be able to do this. And they chose dot because, well, it's one less thing to type than an arrow. But it's common in languages if you can do both, to have a dot refer to something that is static. Right? Because this can be executed. That thing, like if I say that equals 3, requires only, and if these variables are declared as global variables, it requires only one memory access to store the number 3. There's no load for memory required because the compiler knows the address of D0.E. Just like with static array. We'll talk more about this next time. Here, if I want to do this, it requires 2 memory accesses. Now the one is to store the 3 here, but the other one is to read the value of D1. And this is where this arrow is actually kind of helpful. Because if you wanted to know how many memory accesses, every time you traverse an arrow, that's a memory dereference. And every time you traverse a dot, it's not. So here you can say, well, to get from here to here, I have to read the value back from memory. Whereas with arrays, you remember we had B bracket 0 equals 3, and C bracket 0 equals 3. This is a bit confusing because this requires only one memory access because the compiler knows the address of B sub 0. This requires 2, same thing. But you can't use the square bracket as a guide to know whether you're doing a dereference or not. So here, essentially you're dereferencing a constant, so you don't have to read the value from memory. So, any questions? Right, so